don't have
I know.
to.
Yeah.
Okay. Good afternoon. Welcome, ladies and gentlemen. Uh, here, it's my pleasure to introduce our first speaker, Professor John Francis from Northwestern University. He's going to talk about factorization homology. And please join me in welcoming John.
Thank you very much for the introduction, and I really appreciate you all coming to listen to me today. So I'm going to start off and spend most of the time talking about the following theorem, which is joint work with my collaborators, David Ayala and Hiro Lee Tanaka. So this theorem, which I'll spend a lot of time unpacking, I'll just put it up here for reference. So this says that there's some collection of objects, some kind of homology theories. And these are homology theories for three-dimensional manifolds with one-dimensional submanifolds, all of which are framed. So these are some kind of like knot or link homology theories of a certain type that have certain structure and satisfy some conditions. So these things have a relatively simple algebraic characterization. These collection of things, one of these homology theories is equivalent to a triple. This triple, the first thing, is an E3 algebra. The second thing is just an associative algebra. And the third datum in this triple is a map from the Hochschild homology of the E3 algebra to the Hochschild cohomology of the E2 algebra, where this is an E2 algebra morphism. So it's not the simplest piece of algebra in the world, but it's a lot less data than telling you what one of these things does on every possible three-manifold with every possible link inside of it. And this will go through an intermediate step where we'll show, well, where both of these are equivalent to what I'll call maybe disk algebras over disk 1 in n framed. Okay, so that's the result. This is from our paper, Factorization Homology of Stratified Spaces. And so we really prove a result that's kind of like this for every stratified space. We kind of characterize certain kinds of tensor homology theories on those. But I'm just going to talk about a relatively simple case today compared to that, which is just in the case where the stratification is a one-dimensional submanifold and the manifold is a three-manifold. But you could think that there's a pretty substantial generalization of this if you're interested. All right, so just to say this in words, let me put below. So this says that these sort of tensor homology theories for links, for framed links in three manifolds. So these we'll see are things, some functors from this to a category of chain complexes over K, which satisfy sort of a multiplicative version of excision, which we call tensor excision. So this, we'll say, characterizes these tensor homology theories for links. All right, so that's what I'm going to talk about, and now I'll just tell you more or less what each piece in this statement means. Any questions before I go on? Yeah. Oh, that's right. N, I'm restricting to N is 3. Thank you. Here. All right, so I will start off with what this means. So let's start off just where there's no one-dimensional submanifold. So manifold N, this will have objects that are smooth N manifolds without boundary. And the morphisms, well, it'll have mapping spaces, and the mapping spaces in manifold N from some N manifold M to another N manifold M, this will be the space of embeddings from M to N. So this is forms a topological space, and this is a by what's known as the weak Whitney topology or the compact open smooth topology. Those are just different words for the same thing, where this is, we say that some sequence of embeddings, sort of Fn converges to another embedding F if it does so pointwise and pointwise for all derivatives on compact subspaces of M. Okay. If it converges pointwise and df and all right, so that's what manifold N is. So this is a pretty interesting category, and it's sort of a mixture of very hard and not that hard. So if we just take two arbitrary N manifolds, or let's just say one arbitrary N manifold, then this lets it be closed, then just the space of embeddings from that to itself is the diffeomorphism group. And for a general N manifold, that's a pretty hard thing to understand. And in general, these mapping spaces are always infinite dimensional, as soon as N is above 0. However, I also want to convince you that it's in some ways not so bad. So here's a proposition that I think is one of the most important basic results in differential topology, which is probably pretty familiar to some of you, but it's maybe for some students here, you'll learn it from me, and it's my privilege to be the one to tell you. So we could ask to understand what just embeddings from Rn to Rn are. Just this collection of smooth embeddings from Rn to Rn. And this, as a topological space, it's complicated. It's very infinite dimensional, and there are a lot of embeddings. But you could just choose a point in Rn, and you could take its derivative. And that's just a linear map now from Rn to Rn. And then you could actually just turn it into an orthogonal matrix. And that procedure actually gives you a homotopy equivalence between this space of embeddings from Rn to itself and just the orthogonal group, On. So as a homotopy type, which is really how these spaces, these mapping spaces, will be important to us, this is not so scary. It's like really something that you can understand. So I'll sketch the proof for you. So there is a, let's say, a natural inclusion of GLN just consisting of those which are linear and send the origin to the origin, say. And there's actually a deformation retraction. So there's a map from embeddings of Rn to Rn to this self-embedding space that, at time 1 just gives you is the identity. It just sends F to F. And then at time 0, it'll give you something linear. So it'll send F t to F sub t, where ft of x is f of tx over t. If t is greater than 0, in the derivative of f at 0 when t is 0. And since the limit of this is exactly this, as t tends to 0, this gives you a continuous expression that's pretty well behaved. So that proves that, that this is a homotopy equivalence. And then this further equivalence to ON is Graham-Schmidt orthogonalization. So that's my proof sketch. And this might look, if you haven't seen it before exactly like this, it might look pretty familiar because it's basically in Milner's topology from a differentiable viewpoint. There he proves that every diffeomorphism of Rn, is smoothly homotopic to either 1 or -1, the two components here. But if you went to the trouble of defining what the topology on this mapping space is, he's really proving something stronger. Okay, so that's not so bad. So there's an elaboration of this argument. Sorry. It's actually not so bad to describe the embeddings of Rn into any n-manifold. So if we just choose some general n, then taking the derivative at 0 gives you a trivialization of the tangent space. In other words, a framing of some of one of the tangent spaces in n. And so that gives you a map to the frame bundle. Of the tangent bundle. And that is, again, is a homotopy equivalence. So just if you're just starting with trying to map out of a Euclidean space, the homotopy types that you get here are things that you can work with. So they're not as infinite dimensional as they look at first. This is a finite dimensional principal bundle over a manifold. Okay, any questions? All right, so that's without the, so that tells you what manifold 3 is without the 1. And now, say manifold K and N, this will have objects, a K-dimensional submanifold of an N-manifold, Definitely, I'll get there. Yeah, sorry, who asked that? The framing? No, there's no framing there. It's the frame bundle. Well, you're asking what the frame bundle is? Sure. So the frame bundle consists of so a point in the frame bundle is a point, say P in N, with a trivialization of the tangent space at P. Say it again? Oh, well, if you choose a Riemannian metric, then you can ask it to be orthogonal. Those two things will be homotopy equivalent. So this statement is just about a homotopy equivalence. Yeah. Right, it won't matter. But for this statement, all right, and the morphisms. Will sit inside embeddings from M to N, such that K embeds into L, and so consisting of those F, such that F sends the subspace K to the subspace L, and K is indeed F inverse of L. Okay, so in other words, if N was 3 and this is 1, those are those embeddings that preserve the knot. So there's again, these mapping spaces look infinite dimensional, but similarly they're not so bad. So the more or less the same argument here, if you want to understand the basic pieces, this is homotopy equivalent to just a product of orthogonal groups, O of K and O of N minus K, by more or less the same argument. And if this submanifold is empty, in other words, I'll just write it like this just for the moment, if it's the empty k-dimensional submanifold in Rn, then this is just embeddings, or I'll say this for any. This is just embeddings of Rn into the complement. Which we've described previously. All right, so that concludes the definition of just what manifold 1 and 3 is. Now, I'll talk about this framed part. Any questions before I go on? Yeah. So, by this you mean like that? That? Yeah. Yeah. You'd want to be a little bit careful about what you meant by men, but yeah, not just framed, but Well, framed actually makes it a little easier, but just like what submanifolds are and stuff. Yeah, the answer is the same. But in this particular case of 1 and 3, then actually everything is the same since 3 manifolds have essentially unique smooth structures and I'm about to. Yeah. Okay. Framing. So framing of an n-manifold is just an isomorphism of vector bundles between the tangent bundle and a trivial rank n bundle. So in particular, it's an identification of the tangent space with a choice of n independent vectors in the tangent space consistently for every point p. So. So now what's the space of framed embeddings? The space of framed embeddings is going to sit in a square. It will consist of an embedding in particular. And it will also consist of a map from M to N. And these, given an embedding, there's a map of vector bundles from the tangent bundle of M to the tangent bundle of N. And also given a map from M to N, there's such a map of vector bundles just using the identifications that both of these have a trivialization. And so it'll just be this sends, we'll say, F goes to M times Rn to N times Rn. I'm going to put this. This map sends F to use the framing to identify M with M times Rn. Then use F times the identity as a map to M times Rn. Then use the framing to identify that with the tangent bundle of Rn. And all of this lies over the map F from M to N. So that use of the framing gives you a map from this space of maps from M to N to this space of maps of vector bundles. And so it's this homotopy pullback. So in other words, it's a choice of a map, it's a choice of an embedding, and then it's a path between the associated map of vector bundles from the derivative of the map F to this map. And it's important that it's a path right here because if I just said that it was the actual pullback, in other words, that's saying that the map preserves the framing on the nose, then this becomes a very rigid notion. And in particular, these framed embeddings will be isometries. But so here framing is a very flexible notion, and we're allowing ourselves this path from one to the next, and that'll be kind of important for us. So this makes the definition more complicated, but it makes the sorts of homotopy types you encounter easier. So now, the space of framed embeddings from Rn to Rn is contractible. Its homotopy equivalent to a point. And if we're given some framed n manifold, n, the space more generally, the space of framed embeddings from Rn to n is homotopy equivalent to n itself. So we're getting a little bit simpler answers. We've sort of gotten rid of the orthogonal groups that were appearing in our previous answers. So that's what the framing does for us. Okay, so likewise, if we have K and M framed, so this means that K is framed, M is framed, and the normal bundle is framed. No, in such a way that the sum of this framing and that framing is equal to this framing. So in a compatible way, then we can define this in the same way, the space of framed embeddings. Well, I'll just say is defined similarly. So it's an embedding of this into this, and a path between the pulled back framing along that embedding and the given framing here. Okay, so now the object of interest, this category of manifolds, has objects, these framed k-dimensional submanifolds of n manifolds, and morphisms, which are these framed embeddings. Okay, so that completes 1. Any questions about 1? So I think what I'd like to, okay, so 2. An E3 algebra well, is a functor. First, I'll define disk n framed. Will just be a subcategory of manifold n framed with the objects are finite disjoint unions of Euclidean spaces. So an EN algebra so that's what disk n framed is, and then an EN algebra, let's say in K modules, is a symmetric monoidal. Functor from disk n framed to k modules. Call this, say, F. So A, the underlying algebra, is just the value of F on a single Euclidean space. And then note that this comes with the structure by being a functor, then more generally, since it's symmetric monoidal, that's with respect to disjoint union there, then that determines all of the other values. So that's sort of why you should think of this as being algebra, even though it seems like many more objects. They're all just determined by the value on Rn. And this comes with a certain structure, namely, by a functor like this, what that means is that, say, there's a map from chains on this space of framed embeddings to this chain complex of homs from A tensor to the I to A. And so in particular, for every choice of a framed embedding, you get a multiplication. So for, in this case, where I is 2, the space of framed embeddings of 2 copies of Rn into Rn, remember, we could say, just send one of these, assume since Rn is contractible that it goes to 0, and then evaluate the other one at 0, and that gives you some point that's non-zero in Rn. So this has the homotopy type of Sn minus 1. So you get a map from chains on Sn minus 1 to homs from A tensor 2 to A. And this has 2 homology groups, one in degree 0 and one in degree n minus 1. And so in degree 0, you get an algebra structure. And in degree n minus 1, you get a Lie algebra structure, a Lie bracket. And these Poisson commute appropriately interpreted. So you could think of these En algebras as some kind of a deformation of an n Poisson algebra. Okay, so that's what that. So in particular for n, when n is 3, that's what that E3 algebra is. So, it's a commutative algebra as soon as n is at least 2. It's a commutative algebra at the level of homology. These are okay. So I'll pause for a moment on what the rest of this means and tell you the disk 1-3. So disk, say 1n framed, is just the full subcategory of manifold 1n framed. Where the objects are either finite disjoint unions of, well, there's Rn, where the one-dimensional submanifold is empty, and then there's Rn with a line in it. And everything else is just a disjoint union of some number of each of those factors. So let's just think a little about the structure that these things have. If we're given now, well, a disk, let me also define what a disk in algebra is. So this is, again, a symmetric monoidal functor. From this category to, let's say, chain complexes over K, some ring K. And now note that everything is disjoint unions of just two objects here. So at the level of objects, this is just determined by what happens on Rn and what happens on Rn with a line in it. So note that objects by the value A, which is f of Rn, and B, which is f of Rn with a line in it. And I claim that this is an En algebra. And this is an algebra. The algebra structure here coming from composing the lines. And then you mean, sorry, you're asking how that's an algebra? So here's the algebra structure. So we can consider this disjoint union, R1 and Rn. And there are maps, R1 and Rn, where, let's just say if here's, yeah, exactly. So if this one is, let's say, blue, and this one's yellow, then we just can shrink things. And these spaces of embeddings are contractible, once we've chosen an order, just like with an algebra. Thank you. Yeah. So that gives it an algebra. But now let me. So there in order to make it simple, I drew it in 2 dimensions, but it's now going to be convenient to think about this structure to actually draw the n equals 3 case. Yeah. Yeah, so there's a coherence theorem that says that algebra is up to homotopy. can be strictified to produce an actual algebra. So when I make that little, I use that little symbol, equivalent, homotopy equivalent to, so to go from there to there would be a strictification procedure if you wanted. Okay, so now in this, this structure, so that we have this En algebra, this E1 algebra, and now there's an action. I want to just see what this action looks like. So note that there's so if this is so if here is Rn with a line in it, and I haven't, let's make one of this to be 3. So note that I can embed a ball here in R3. And we can take this R3 and I can move it around the line. So we see that there's sort of an S1 family of embeddings around R1 and Rn. And so that is like, and so that when we apply the functor f, this gives an S1 family So for this symmetrical nodal functor, this gives us an S1 family of actions, but even better, central actions of A, the value on R3, on the algebra B, the value on R3 with a line. So this this structure, so part of this theorem, is that such a structure, an S1 family of central actions of A on B, this is equivalent to, I'll just use that to indicate that sentence, to, well, a map from this thing that I guess I haven't said yet, the factorization homology of A to the Hochschild cohomology of B. So the Hochschild cohomology is a derived version of the center, so that's where this central part is coming. That's why it's not just a map to B. And this is equivalent to Hochschild homology. So that's why we get a map from the Hochschild homology of A to the Hochschild cohomology of B. Yeah, so it's right. So for each point in S1, that B is an algebra in A modules. Yeah. Okay. So where, and I as well say that this is implemented. I'll give this a name now. by factorization homology. And I'll use an integral sign because it's supposed to be some kind of algebraic form of integration that says that this value for this A, this triple, we'll say corresponds to a script A here. This is the colimit over U and the overcategory of 1, 3 disks embedded in M and K of the value A of U. This homotopy colimit. So it's a derived expression. In the particular case when M is S1 or S1 times R2 and K is empty, you get Hochschild homology back. All right, so that's what I wanted to say about this theorem. So you might ask now, well, what does this have to do with other sorts of knot homology theories or other invariants of knots that maybe you've heard about? So before I say something about any other questions before I go on? No, there's a version that's for any tangential structure. I chose to just talk about it for frame today because the resulting algebra is the simplest in the framed case. So there's a construction. And this is joint work with Kevin Costello. And Owen William. So given a semi-simple Lie algebra with invariant pairing, there exists an E3 algebra. I'll call it A, which is, I'll say, an E3 deformation over H bar of the quantum group, UH bar of G. Further, and they'll say that this is like Cazul dual. So in the sense that Lie algebra cohomology, E3 deformation of, what I meant to say, this is an E3 deformation of Lie algebra cohomology. And this is sort of Cazul dual to the quantum group, where H bar is a formal parameter. In the same sense that just Lie algebra cohomology is Cazul dual as an associative algebra to just the enveloping algebra of G. So there's a sort of an E3 version of that. And using that, there exists such an E3 algebra. Further, continuing this construction, for V, a finite dimensional representation of UH bar G, there exists a disk 3-1 algebra, call it A sub V, where the E3 algebra part is this A, and the The associative algebra part is endomorphisms of G, of V, over UH bar of G. To this? Yeah, the Lie algebra cohomology is a commutative algebra. Yes, this deformation this is a deformation of this as a commutative algebra to an E3 algebra. If you set H bar to 0, you'll get this back. But the algebra over H bar is just an E3 algebra, not commutative. Sorry, I don't have much time, so let me finish. So, but I'd be happy to come back to it afterward. So there's this E3-1 algebra. Yeah. There's this disk 3-1 algebra. And also part of this, construction continued is that there is a trace map from this resulting factorization homology of this A sub V to just the factorization homology of M. And this is a unital algebra, so it has a unit map from the ground ring. And this composite gives an element that I'll write the integral over trace of V of K in M. Now, this is this is an interesting invariant, but I'm just telling you that it exists in some object that you maybe have never thought about before. However, this becomes something pretty familiar if you're just considering knots in R3. So for M equal R3, we get an element, this sort of integral of the trace of V in R3 of A, and this is just equivalent to A, which, just as a complex, is cochains on G on H bar, so you just see C adjoin H bar in degree 0, and this lives in degree 0, so you're getting some series in H bar. And so the theorem is that this is equal to the Reshetik and Turayev invariant. So we did this a while ago, and we're finally writing it up. So I'm optimistic that it'll be out soon. That's what you get. Pardon me? That's an R3. Okay, thanks. Yeah. Okay, so this produces these interesting knot invariants, but just in the case when H bar was a formal parameter. You might ask, what about more general? There's this thing called the Tangle hypothesis that produces sort of more general knot invariants. How do you produce that? By this kind of integration procedure? And that's you need a sort of a fancier version of factorization homology that David Ayala and I have been working on, and that's in preparation. So thank you very much for your attention.
Any question?
Thank you very much for your talk. I have a question related with the Reshetik and Turayev, because typically this is defined over some molar category. I mean, depends of some additional. And here, what is the category? It's directly related with the.
This is the not invariant. So this is the not invariant that is just
I
given
see.
by a dualizable object.
The not invariant.
Yeah, this is a not invariant.
I see. I see. Thank you.
I can repeat the same question. So it looks like from what you're saying that UH of G, this quantum deformation, has some extra structure which is weaker than. I mean, causal duality is, after all, about causal duality of algebras.
So it's not a. So maybe I should have put causal dual in quotation marks. You should think of it as being the causal dual. It's not that on the nose, but it bears a similar relationship.
Thank you very much. I wonder what's the tensor excitation here in the definition for like tensor homology theories. Is it by cutting R3 into like using R2 slices of R2?
Yeah, that's a good question. So tensor excision. So I'll just say it without the one manifold, just for the three manifold. So it says if we have M, which is expressed as a gluing of M prime and M double prime along a codimension one submanifold, that this value, f of M, is equivalent to the value of f of M prime, the value of f of M double prime, tensored over this object, and it's the derived tensor product over this. So this inherits the structure of an algebra from R, and you can make these two things left and right modules over that. And so you're asking, then there's a natural map from there to there, and you're asking for that's an equivalence. So it's it says that these values are determined every time you have a codimension one cut. And if there was a one manifold in there, then you would require it to be transverse to the one manifold.
Thank you very much. So we're really considering a cobordism category of two-dimensional manifolds, where the cobordisms are three-dimensional.
This is not a cobordism category.
Yeah,
it's related, and so you can get things that are like bordism theories from this, because from this you can produce such a thing, but there's some extra steps there.
Yeah, I see. So what we can say about I wonder what we can say about theories like Khovanov homology, where we're actually considering four-dimensional cobordisms of three-dimensional manifolds with a link in it, and where the links are connected by a two-dimensional surface.
You don't get Khovanov homology from this. It doesn't have the right naturality, but maybe from the beta version that I was mentioning, but that's to be determined.
Another question?
So you explain E3 algebra A and B in your example. So can you say a bit words on the phi? So what's the structure goes into the definition of phi? So in your example, in the last example of.
You're asking how we got phi there?
Phi.
Yeah, so what I described was in this, so the way that this is proved is that, well, we prove this equivalence, and I didn't say too much about it, but roughly we give a functor here, this factorization homology procedure, and then we show that it satisfies these axioms, and therefore it's unique. So that produces an equivalence. And then we describe what this algebra structure is. There are two objects, and an E3 algebra, an algebra, and then a suitable action of one on the other. And that action is like an S1 family of central actions of the E3 algebra on the algebra. And so the last part of the theorem is that an S1 family of central actions is equivalent to phi.
Yeah. So in your explicit example about not invariant in, so is there the phi is mean, you construct this A and B very explicitly just on the board. So the phi is something general or something explicitly as in terms of quantum group, say.
In this example.
Yeah, in this example.
In this example, so where does phi come from? Yeah, it's, I'm not sure how to say it quickly. Sorry.
Okay, thank you, John, for your fantastic talk.
Oh, thank you.
Thank you.